is polynomial functions of a higher degree and being able to model them. Okay, so when we talk higher degree, we've already done the linear, so the x to the first. We've already done the quadratic, the x to the seconds. Today's focus is going to be more on x to the thirds and x to the fourths. Okay, so our cubic and quartic functions. A little bit of vocabulary up here. Polynomial is made up of a sum or difference of individual monomial terms. These terms are written in standard form, which is descending degree, which we'll kind of talk about that as we go through. So just remember standard form being the idea of highest power to lower power. Leading coefficient is always going to be that number out front of the highest powered term. And then constant term will always be at the end. Okay? Now, with example 1, we're going to think about these in terms of transformations. So the idea here that on A, I see an x to the third equation. On B, I see an x to the fourth equation. And we'll talk about what those look like as we go throughout the lesson. But then being able to transform these. So first of all, we are asked to describe. So that's going to be putting our words down. How to transform the graph of the monomial function into the graph of the given function. And then support your answer graphically, compute your y-intercept as a check. So we're going to talk about how to graph this by hand. And we can use the calculator also as a check. But as you look at A, g of x equals 4 times x plus 1 to the third. What are the pieces you see? What? The 4. What's the 4 do to the graph? Now, when you're multiplying by a value out front, it's going to be a vertical, well, when you're multiplying by a value bigger than 1, vertical stretch, right? So we're going to have a vertical stretch by a factor of 4. What else? What about the 1? Okay, it's a plus 1 inside the parentheses with the x, so it's left or right opposite the sign. So we're going to be taking this graph left 1. What is the basic graph we're talking about here? X to the third. Okay, so when I write out my description, I am going to mention that this is x to the third. So we're going to translate that graph left 1. And that's the graph of y equals x to the third, and vertical stretch by a factor of 4. So I'm going to write this in words, and then we'll actually make it happen. Translate or shift. Translate graph of y equals x to the third, left 1 unit, and vertical stretch by a factor of 4. Okay. So that is your describe part. Remember, anytime you see describe, we're looking to put it into words. Okay, let's think here. Okay. Ooh, I didn't make this graph very big, did I? I don't really need to be able to go left or right very far. So I'm just going to go mark out 3 on each side. Now, to do the original graph, which is what I want to start off with, I am going to mark off up and down 8. Because what I want us to think about is start with the basics. What points does y equal x cubed have? think he kind of had the shape. Think about what points does it go through. If you put 0 in, it's going to go through what? Do I have room here? Yeah. If you put 0 in, it goes through 0. If you put 1 in, 1 cubed is 1. If you put 2 in, 2 cubed is 8. What if I put -1 in? -1 times -1 times -1 is -1. What is -2 to the third? -8. Okay, so remember, you can always, you can probably come up with the basic shape in your brain, but you can always make that basic XY chart, right? So if I think about those basic points, and I'm just going to kind of put them on here so I have the basics. 0, 0, 1, 1, 2, 8, -1, -1, -2, -8. I'm just going to kind of do a dotted line through there, or maybe oh well, I already put on there. But we want to take this graph and we want to transform it. Let's go over here. Now, we can do, because it's left to right, or it's left, and it's a stretch, we can do either of these first. It doesn't matter which one you do. Okay? 0, 0. Do you remember how to do the stretch by 4? What's that going to be? In order to do a vertical stretch by 4, what is it we multiply by 4? The y values, right? So that's going to be taking each of these and multiplying each of those y values by 4, right? This sounds familiar? And then, so like 0, 0. 0, 0, when you multiply the y value by 4, is still going to be 0, 0, yes? And then what happens then when you move that point? We also have to move that point left 1. So 0, 0, which would stay at 0, 0 with the stretch, and now goes left 1. Am I okay to do this all at once, or is this going to be too much? This might be too much. I don't know. Okay. 1, 1 would become what? 1, 4 when I vertically stretch, right? So 1, 1 really becomes 1, 4. But with a shift of left 1, it's going to go right here. Are we seeing that? 2, 8 becomes 2, 32. I'm not going to graph that. I mean, you can, but I'm not set up to graph 32, am I? I mean, it's going to be way up here. I don't know, up there somewhere. Who knows? Okay, -1, -1. When we vertically stretch that by 4, it becomes -1, -4. But then when you move it over 1, it's -2, -4. Okay? And then obviously we could go -2, -32. When you move that left 1, it's -3, -32, but 32 is a little out of my range. So this green graph is going to be my final graph. Can you see the vertical stretch? Is it steeper now? There at the center, it doesn't curve quite as much. It's more straightened out, right? And then my centering point moved left 1. Now, support your answer graphically. We did graph it. You can throw it in the calculator if you want. It also said compute your y-intercept as a check. How do we check it? How do we find a y-intercept? Y-intercepts happen when you put 0 in for x. And so if you were to put 0 in for x, put 0 into this original equation, so g of 0, 4 times 0 plus 1 to the third. Well, 0 plus 1 is 1. 1 to the third is 1, and 4 times 1 is 4. Does that check with where I ended up? And it does, doesn't it? Okay, so y-intercept is always an easy point to check because it's just putting 0 in for x. Okay, questions? Okay, let's try B. What are the transformations you see happening here? Let's describe them. Okay, reflected across the x-axis because there is a negative out front of the whole equation. What else? Up 5 because there's a plus 5 at the end. Right 2 because there's a minus 2 in the parentheses. And all of this is being done to what main equation? X to the 4th, yes? Okay, so I'm going to start with my reflect. Reflect the graph of y equals x to the 4th across the x-axis and translate right 2 and up 5 units. Now, x to the 4th. X to the 3rd, I kind of expected you to have a basic idea of what it looked like. X to the 4th. Have we talked about this one? Do you know this one at all?
No, not to Apple.
And that's fine. As I said, I couldn't remember if we do this one or not. Throw it in your graphing calculator by all means. Whoa.
That's not.
There you go. What's it look like? Looks like a parabola, doesn't it? Now, how is it different from a parabola?
It's
Bottom slider. Now, here's my comparison. In y2, guess what I'm going to type? X squared for comparison. Okay, so that x to the 4th, as Autumn was saying, it's flatter at the bottom, yes? And it ends up going up steeper. Okay, which will make sense when we think about the pieces there. So there's your flatter at the bottom, there's your parabola. Okay, so again, you have the graphing calculators, right? Use them to your advantage. Let's see. With that in mind, looks like I went out about 3 or 4 left and right. Looks like I went up and down about 5. So 1, 2, 3, 4. I'm going to go out 4 on my sides. I'm going to go up and down 5. Not that you can't go more, but. Should we start with the basic graph? You just start with the basic graph. Y equals x to the 4th. Now, can we do this like a parabola? A parabola, we tend to just plug in what? 0, 1, 2, and then reflect, right? I mean, if you want, you can -2, -1, 0, 1, 2. But you plug in 0. 0 to the 4th is 0. What's 1 to the 4th? 1. 2 to the 4th? 16. Okay. -1 to the 4th is also a +1. -2 to the 4th? 16. Okay, so if I have 0, 0, 1, 1, negative 1, 1, I guess I could have gone up 16, but I didn't. Realize it's going to be going up fairly steep, isn't it? Okay, so that's my initial graph. And it's not that you have to graph the initial graph, I just think it's helpful at this point in our lives. Okay. Excuse me. Now this one's a little easier to graph in my opinion because you don't have a stretch. Can you visualize what to do here?
Put it upside down and then translate it.
Yeah. So it's going to go upside down, and then we need to move it right 2 up 5. So can we just take that vertex and move it right 2 up 5? So take your vertex, it was right here, go right 2 up 5. From that vertex, your first set of points go normally over 1, up 1. Now we're going to go over 1, down 1 because we're reflecting upside down. Officially, the next set of points should go where? Over 2, down 16. And so that means, gosh, I can get 10 down, so I guess if I add 6 more marks, I could go 16 down, if I wanted to. But the idea is it's going to be way down there, isn't it? Be like down there and down there. Not that you have to add that, but the point is that this is going to be pretty skinny. It does not get wide as fast as a parabola does. And that's because of the higher power. Okay? So those are a basic x cubed graph, a basic x to the 4th graph. We'll get into some fancier ones here in a bit. Shall we check our y-intercept? Which, yeah, we do know a y-intercept, don't we? So if I put in 0, h of 0 is the negative of 0 minus 2 to the 4th plus 5. 0 minus 2 is negative 2, so it's going to be the negative of negative 2 to the 4th plus 5. Negative 2 to the 4th is going to be 16. It's going to be the negative of that, so negative 16 plus 5, and negative 16 plus 5 is negative 11. Is that where I ended up at? You may or may not have done your y-intercept, but notice I was already at 5. I added 6 more there, so I ended up at negative 11, didn't I? Okay? So just kind of a good little check here. Again, work to be able to do these by hand, but can you check on the calculator? Okay? My recommendation is always try and do it by hand. Write it down, do what you can, and then check with the calculator. Okay? You have that advantage, and that's how we work. Find your mistakes early, right? Okay. Good? Okay, well, let's look at example 2 then. Example 2 is looking at combinations of binomial functions. So here, this was just x to the 3rd, x to the 4th. Just a single function. What happens to it? Okay. Example 2, we're looking at what happens when you combine an x cubed and an x. Okay. Kind of an interesting thought. I don't know that I'd ever thought about before I taught it. But so graph the polynomial function, locate its extrema and zeros, and explain how it's related to the monomials from which it is built. Okay. What do I mean, extrema and zeros? Do you remember those vocab words? Extrema. Okay. Extrema is going to be, we want to talk about its mins and maxes. What are zeros? Where it crosses the x-axis, so your x-intercepts. right? Those words are in your brain somewhere. You just got to pull them out from the back, dust them off. Okay, you've heard those words before. I've taught you those words before. Not saying you remember them. Okay. Sorry, pausing for a moment. I guess what I want you guys to do is I want you to graph this. Yeah. Sorry, I had to think. So throw this in the calculator and see what you get. I was trying to think if there's a way we want to find mins and maxes in Extrema, but there's not. Okay. So let's talk about the first x to the third plus x. What's it look like?
X cubed.
Looks pretty much like x cubed, doesn't it? Okay, we'll examine that a little bit more. Let's talk about Extrema. What do you have in the way of Extrema on this graph? In other words, what do I have in the way of mins and maxes? Do I have a high point, a max on the graph? Do I have a low point, a min on the graph? No. This graph is just one continuous increasing function, isn't it? Does it ever have a min or a max or a min? It doesn't. Okay. So it is okay to say that there are no extrema. Okay. It's going infinitely up, it's going infinitely down, there's no extrema. There's no mountains or valleys along the way. Okay? What about zeros?
Oh, zero.
Where is there a zero at?
Zero.
At 0, yes. Okay. The graph crosses through the x-axis at x equals 0. So there is a 0 at x equals 0. Now, explain how it's related to the monomials from which it's built. So we already talked about this looks a lot like x to the third, doesn't it? Okay. If you look, it's built from x to the third. So as it should look a lot like x to the third, and it's built from x. Okay, so I'm going to put x to the third in here and compare. Are they pretty similar there? Pretty similar, yes, as we already talked about. Now, the other monomial it's built from is y equals x. Okay, we're going to graph that. And then my suggestion is I'm going to zoom in at the origin. So I'm just going to do a basic zoom in where I hit enter an extra time. There's the original. Oh, I graphed in the, never mind. Graphed in the wrong order. Okay, so my black one is my original, x to the third plus x. The blue is x to the third, similar in shape. What do you notice about y equals x?
It doesn't, or like, it doesn't match us.
Okay. Y equals x, it goes straight through 0, but what do you notice with my black graph?
It's
Does it kind of overlap for a bit? Yeah, it's very similar there, isn't it? Okay, if I, okay, if I trace along that y equals x, it almost looks like I'm tracing along my black curve for a bit, doesn't it? Yeah. Okay. And so with that in mind, the idea is that y equals x, what that's doing is it's controlling the behavior of the origin. So basically we have a y equals x cubed curve, but near the origin it has the slope or the shape of y equals x. Okay, and that'll make a little bit more sense when we do the next graph. Okay, so this is just kind of the basics here. So when I talk about how is it related to monomials from which it's graphed, the shape is much like y equals x to the third. Near the origin, the shape or slope is like y equals x. That's what I'm going to put here. The shape is much like y equals x to the third. Near the origin, you can say the shape or slope is like or similar like y equals x. Okay. Get that down. And let's think about B. Go ahead and graph it. And the difference this time is really just one sign, isn't it? So what happens when you do y equals x to the third minus x? Okay, we now get to talk about min and max, right? Your graph does something like that. So we need to talk about extrema and zeros, and then we'll do a description. What do you know about this, the extrema? There are some this time, aren't there? Now, my recommendation, I would zoom in before I try and find my mins and maxes. Okay, so if you don't remember how to find mins and maxes, now's a good time to practice. Okay, I definitely encourage that. So I'm just going to do a basic zoom in because I want to see my graph a little closer. Remember how to find mins and maxes? Second, calc. And if I find my, what comes first? The max. I'm going to do my max first. Left bounds. Remember, I want to go left of that highest point. Hit enter. Right bound. I'm going to go right of that highest point. Hit enter. My guess is I'm technically supposed to go back approximately to that highest point. Your max should match mine, right? In my answer key, I have 2 decimal places. So I have that there is a max at negative 0.58, comma 0.38. You can find the min in a similar fashion, right? Second calc. Go number 3, your minimum. This time, I want to be left of that lowest point for my left bound. Then I'm going to be right of that lowest point for right bound. And my guess is going to the area of that lowest point. Your min should match mine. Do those numbers look familiar? It's symmetric. Okay. So just switch your signs around. There's a min at positive 0.58 and negative 0.38. What about zeros? -1, 0, and 1. Does it look like it? Can you confirm it if you need to or want to? Yeah. And if you do remember second calc, if I just confirm one of them, 0. For your zeros, remember left bound? You go to the left of where it crosses the x-axis. Then you go to the right of where it crosses the x-axis. And then your guess is going back to where it touches the x-axis. That is -1, isn't it? And if you checked, the others would be at 0 and 1. Okay. Let's talk about the shape here. What are your thoughts this time? Does it still have, if I go back to a regular graph, does it still kind of look like x to the third overall? Basically, doesn't it? What's the other piece of this?
A negative x.
And negative x instead of a positive x. So if I do negative x, and I graph it, now, from that view, it's hard to tell. Try zooming in. If I just zoom in, I'm just hitting enter twice to do that. What's happening when you zoom in?
It still follows like at the origin the x.
Yeah.
Or
My blue graph is the original graph this time. My y equals negative x. If you notice at the origin, if I get on there and trace, I'm following the black line, aren't I? Okay, so same thing as last time. Okay, overall the shape is like y equals x third, but near the origin, the slope takes on that of y equals negative x. Okay? So, I'm going to write my pieces down. Shape is like y equals x to the third. But near the origin, the shape or slope resembles y equals negative x. And I guess that's a perfect stopping point, isn't it? Okay. As noted, there is lots of explaining with this, okay? So it's going to take us several days to get through these notes. I'd say there's no way we're getting through the notes tomorrow, which would put the homework due Friday at the soonest, okay?